Hi, grade 12. Now we are looking at part 2 of momentum. So remember, part 1, we explained that whenever an object is moving, then it's got a momentum. As long as there is a velocity on that object, then it's got the momentum. So that is what we have discussed. Then there is the amount of motion on an object. So that is what momentum is all about. So now we want to look at the second part of this concept here. So the second part, it's what we explain whenever now there are two objects involved. So now we are looking at the two objects. It's either those two objects, they are interacting. So whenever there's an interaction between the two objects, so I think that is what I want to emphasize. So now I'm interested on more than one object, but it's always between the two objects. So we call this is a system. So now it's our system that we're going to be focusing on. So when we're looking at this one, we apply this law, then of which says it's a law of conservation of linear momentum. So I must rectify this. We are focusing on linear momentum because it's a momentum of on the same plane. So that's why we say it's a linear momentum. So now, what is the law of conservation of momentum state? Then it states that the total, not the linear momentum, but the total linear momentum in an isolated system remain constant. So these are the key points that we must always remember when we're talking about this thing. What we mean by a total linear momentum, we're saying whenever we're adding the momentum of this and the momentum of that, before it's collide or before it's interact, will be the same momentum after it's interacted or it's collided. Whenever there's a collision, we're introducing the new concept now when we talk about the collision, because in order for this to interact, there must be a collision here. So then we are saying whenever there is a collision, then we always apply this law of conservation of linear momentum. So what does this law state? It states that their momentum of each object when we adding together before they collide. So remember, this is before and then there is an after interaction. So we call this is an after. Another word we're gonna use is initial. So we're gonna say initial. So remember, initial is a beginning. So, or we can also use this term when you say final. So therefore, we are saying the momentum, the total momentum before, then will be equal to the total momentum after, provided that the system is isolated. So what is isolated? So another term we use, we say in closed system, whenever the system is closed. So what is the meaning of this? So the meaning of this term, it say then we assume there is no external forces. There is no external forces. Nothing disturb. There is no external forces here. So it means the system, it did not get disturbed. So it means there is nothing lost there. So that is what we are talking about. Whenever then these two are interacting, nothing disturbed them. So there was not that ball that was colliding with them during their collision, or there was nobody interfering with them as they are colliding. So it's only two of them. Nothing else then is disturbing these two balls. Then we are saying now that total momentum before and then the momentum they have after is going to be the same. So that is very important. So now how do we express that? So this is what the law of conservation of momentum states. It says the sum of momentum. Now remember the total. The sum of momentum before the collision will be equal to the sum of momentum after the collision. So here we are donating initial and then final. So we are saying initial, remember it's the same thing as before. We are donating F for the final. We are saying the momentum after the collision. So now how do we write the momentum? Remember there are two objects, but each object is having its own momentum. So that's why we are writing the formula as like that. This is a momentum of the first object, mass number 1, V number 1, I. So we are saying this is the first object its initial momentum. What was it? Then this is a second object because they are interacting. So this is a before situation. Before they interact, what is the momentum of object number 2? What is the momentum of object number 1? Then after interaction, we are focusing on that. What is the momentum of the object number 1 after the collision? What is the momentum of object number 2 after the collision? So that is what we're talking about here, the law of conservation of momentum. We are saying the momentum remain constant, remain conserved during that collision when we are talking about the isolated system. That's very, very important to remember. This is only valid only if the system is closed or is an isolated system. So if the system is not isolated, it's not closed, we cannot claim that the momentum was conserved. All right, so now let's look at the types of collision that can happen in our real life. So the types of collision that can happen in our real life, we can have the scenario number 1 where two objects are coming from opposite direction, they come to collide and then they can separate by going back in the opposite direction. So that is what to be the scenario number 1 that we can have. So remember, this is a formula for the whole concept of linear momentum, no matter what types of collision you are having. But it's important then to understand that the law of conservation of momentum is state this remain true. So that is very, very important to remember that. So then scenario number 2 that we might have whenever there's a collision, then we can have a situation where the two objects, they are coming together from opposite direction again, but then maybe someone else is having a higher momentum than the other, then they collide and then the first object remain constant, the other one moves. So this one becomes stationary here, or let me just use rest because it's going to be easier to write that. So then this become rest. So then after collision, so that is what we can see. So what normally happens here, the velocity of this is going to be 0 because it's become rest. So then the velocity of this, it's going to be unknown. So that is a scenario number 2 that we might have. Scenario number 3, then we can have a situation where one object is moving and the other object is not moving, and then after collision they combine together, they move like that. So what is important is that if objects move together, so it's important to take note or to remember that their velocity is the same. So this is important to take note, because in other cases then we'll have a situation like that, then where objects are moving together, then you must know that their velocity will be the same. So that is very important. Then another situation, another scenario that I did not put here, but then we can have a scenario where maybe two objects were at rest, like a bomb. Think about the bomb. Maybe two objects were at rest together, then before the collision, maybe before they explode. Think about an explosion. So this is a situation of an explosion. So in most cases, an explosion scenario here. Then after the collision, then they move. It's either in a separate direction like that because they exploded. So it's important to understand about this scenario. Whenever something that's stationary, the velocity is going to be 0. Then whenever they're moving, their velocity, if they're moving together, their velocity will be the same. That's very important to understand that. All right, so let's look at the example of how this can be applied in an exam question, or how can this be asked in an exam question. So number 1, when you're looking at this one, we read the question and understand what it's given to us. Then what is given to us here is that a girl with a mass of 30 kilogram runs at a speed or at the velocity of 5 meters per second, then is jumping on a 2 kilogram skateboard that is at rest. So those are the key information that you extract every time whenever you are reading the statement. Then the question, they say calculate the velocity of the skateboard and of the with the girl after he jumps on it. So now let's understand this so that we can have a better solution to the question. So number one, I'm using the circle. This is my girl, of which is running or is jumping with the speed of 5 meters per second on a stationary skateboard. So this is a skateboard, this is stationary, so it means the velocity is going to be 0. So then after jumping to that, what's going to happen? After jumping to that, what's going to happen is that the girl will be on top of the skateboard. So this is going to be the girl and with the skateboard. So they'll be moving together. So they'll be moving together. So this is going to be the final scenario on that situation there. So now we're applying the law of conservation of momentum. So it stated that the momentum of this object before it collide. So I'm just going to say the momentum of the girl before collision plus the momentum of the skateboard before collision. So the total momentum before they interact or before interaction. Then you see now after interaction they must be equal if the system is conserved. Then but interestingly here is that these two objects are moving together. So whenever they're moving together, what's going to happen? They will have the same velocity. So they'll be having the same velocity. So here I'll be saying the momentum of the girl, the velocity final, velocity of the girl final plus the momentum of the skateboard, then the velocity, it's a mass times that of that. But because these are moving together, I can rewrite this because the speed of this one will be the same. So it means this speed and that speed is the same because they are moving together. So it means now I can simply rewrite this in that form of like that because it's the same speed. I can write that it's the same velocity because they're moving together. So now let's substitute here. What is the mass of a girl? Then it's been given as 30. Then this is 5. Then plus the mass of the skateboard is 2. Then the velocity is 0 because it's stationary. So now instead of writing all this, I can just use this simplified version. So but if you did that, it's okay as long as you still remember that these are the same thing. So now this is going to be 30 plus 2, then VF. So then this is going to be simplified as 150. This is going to be 32 VF. So it means I divide by 32 on both sides. When I divide by 32 on both sides, what's going to be my VF here? 150 divided by 32, then it's going to give me 4,69. So what I'm getting here, I'm getting that the VF will be 4,69 meters per second. So that is what's going to happen. It's the 4,69 per second in the same direction. Same direction. So same direction. It's important because they did not specify exactly where the girl was jumping. Whether I was jumping the boat in this direction or that direction, I don't know. But then that's why I'm just going to use in the same direction to indicate where the velocity of that. So what is this 4,69? Is the velocity of a girl and the skateboard together after the girl have jumped on it. So they're moving with that velocity. So that's very important. All right. So now let's look at number 2. So number 2, what is number 2 says? Then it says that 2 blocks of a mass of 2 kilogram and 5 kilogram respectively move towards each other or on a horizontal frictionless. So it means there is no force by the surface with a velocity of 3 meters per second to the right and then 2 meters per second to the left. So as shown in the diagram below. So after the collision, then the blocks collide. So then after the collision, 2 kilogram blocks moves to the left at 1 meters per second. Then calculate the velocity of 5 kilogram block. So now let's see how can we solve this. So when we are solving this again, we're gonna apply the principle of linear momentum, conservation of linear momentum. So what does it say? It says that the momentum of object number 1 then plus the momentum of object number 2 before it's collide will be the same as the momentum of object number 1 after collision plus the momentum of object number 2 after collision. So now what is very important now before you can do the substitution is that you must always be careful about the direction here, because they specify the direction. I got the right, I got the left. So now you can use your own sign conversion here. In most cases we prefer right as positive and then left as negative, so it doesn't matter if you prepare otherwise. So it means this is going to be plus, this is going to be minus, this is going to be minus because it goes to the left. So therefore, as I'm substituting here, number 1 is 2 kilogram, then it's going to be 3, then plus number 2, then it's 5 kilogram, then it's going to be minus 2, then equal to number 1, we said it's 2 kilogram, then they told us that it's moved to the left now, so it means it's going to be minus 1. Then we substitute the mass number 2, it's 5 kilogram. The velocity we don't know, so I'm just going to call this is VF. So now when you calculate this is going to be 6, then this is going to be minus 10 equal to negative 2, then plus 5 VF. So then we do our maths here. This is going to be negative 4, then plus that is going to be negative 2 equal to 5 VF. Then we divide by 5 on both sides. Then we find our answer is going to be equal to 2 divided by 5. That's going to be equal to what? 0.4 meters per second. But remember now it's going to be negative. So now it's going to be negative. So when it's negative, so what that means? It means that therefore this is going to be 0.4 meters per second to the left, because our negative means left direction. So that is what it's going to be mean by that. All right, then example number 3. So let's look at that example. How can we approach it again? So when you're looking at this one, they are telling us that there is 75 kilogram of the fisherman. Then that fisherman is what? In a boat, there is 125 kilogram. Then, but there's something happening here. Then the fisherman throws a package of a mass of 5 kilogram horizontally towards the right with the speed of 4 meters per second. So then this is very important part. The boat is at rest. So the boat is at rest before the package was thrown. So now let's understand this scenario here. So when you're looking at this, we are looking at this system here. There are 3 objects they are talking about in this scenario. So number 1, we're looking at this one. This is before. Then we got the boat that is here. Then this is my boat, is a beautiful one. And then that boat, there is a fisherman. So this is a fisherman here, and the fisherman is having an object. So that was an object that was thrown by a fisherman. So this is a fisherman, then it's having that object. So before anything happened, this it's they exist as a one system, of which, because they're at rest, then we are saying their initial velocity was 0. So what is this? It's the boat, it's the fisherman, then it's an object that it's a package that was thrown away there. We don't know what type of package was that. So this is before the throw. So now when they're throwing, we got a boat, then with the fisherman, and then we got a package. Then the package was thrown in this direction, or with the speed of 4 meters per second, with the velocity of 4 meters per second. So this is what we have. So now we're gonna look at this as a one object. Then we're gonna look at this. This is another object, because this, remember this is remain in one. This remain as a system because the fisherman is still in the boat even after throwing that. So the only thing that was left was the package. So therefore, it means we're gonna look at this as two objects. As this is object number 1, of which is the fisherman and the boat. Then object number 2, then it's the package. So now when we're applying the law of conservation of momentum, then we're gonna apply it. It's the now mass object number 1, velocity object number 1 initial plus the mass object number 2, velocity of object number 2 initial, then must be equal to the mass object number 1, velocity object number 1, but we call this is final, then plus I think my space, it's giving me a problem here. Let me write it in a bigger space. Sorry about that. So I'm gonna write it here. Mass number 1 and velocity number 1 initial plus the mass times velocity number 2 initial, then must be equal to the mass number 1 velocity of an object number 1, but after they throwing the object, plus the momentum of that, of which is given as mass number 2 velocity number 2 final. So that is what we have. But then now let's understand. Remember, when I'm looking at an object number 1, I'm looking at the boat and the fisherman. So I'm treating this as what? As a one system. So remember what I said. So I'm looking at this as a one object, because after the incident they remain together. So I'm looking at that as one object. So now when I'm looking at that, then I'm looking at 75 plus 125. That's gonna be 200 kilogram. So I hope my mathematics is serving me right there. That's gonna be 200 kilogram. Then the velocity is 0 because it's at rest before the package was thrown. So object number 2 is the mass of a package. So the mass of a package, they said it's 5 kilogram. So it means, and then before it was thrown, then all of them were at rest. So it means it's going to be 0. Then here, then I'm looking at after it's thrown, then it's going to be the mass object number 1, of which is going to be 200 kilogram. Then the velocity of this, I don't know. So I don't know the velocity of this one. The mass of the package is 5. Then the velocity to the right, remember I'm going to use my sign conversion. So here, so now to the right, I'm going to refer right as positive. So I'm referring right as positive. So it means negative is going to be left. So it means here I'm going to substitute positive 4 because it's going to the right. So 200 times 0 is going to be 0. Then 5 times 0 is going to be 0. So all of this becomes 0. Then here I got 200 VF, then plus 20, because this is going to be 5 times 4. This is going to be 20 here. then what I'm going to be having, VF is going to be negative 20 then over 200. That means my VF, remember this is going to be negative 20 divided by 200. I'm using my calculator here. Then what's going to be the answer for that? That's going to be 0,1, negative 0,1 meters per second, but I can't leave my answer negative, so it means it's going to be 0,1 meters per second, but to the left, because negative means to the left. All right, grade 12, as we continue with our second part of momentum. So now we're just going to look at types of collision. There are two major type of collision that we're going to discuss here, what they mean. So we're just going to talk about what's the meaning of it, so that we see how that can be applied in an examination, during the examination. So number one, remember, whenever two objects they collide, it's either they collide elastic, or it's an inelastic collision. So now, what is an elastic collision? So here, in an elastic collision, both momentum and kinetic energy are conserved. So that is what is important here. So what we mean this, the total linear momentum of a system remain the same, but at the same time, we are saying the kinetic energy initial must be equal to the sum of kinetic energy final. So that is what is, there are two conditions here for the collision to be classified as an elastic. So normally how this can you understand it is that whenever there's a collision, if they are telling you that the collision it's elastic, so it means this is true. The total kinetic energy, remember, I will be having object number one, is object number one and object number two. They are coming into collision. Then when they are colliding, so I'm having object number one here, it's coming into collision with object number two. Then after collision, maybe something happened. So this is after collision, maybe object number two and one, they are moving together or whatsoever. So we are saying the total kinetic energy before, then total kinetic energy after must be the same. So that is what we mean by its concept. So some characteristics, some collision, how can you see that they are elastic in nature? For example, without doing the calculation, is that normally the object whenever they involve in a collision, they don't deform, or they don't stick together, or and there's a little to the energy that is lost. So that is what we are saying whenever we say kinetic energy is conserved. So we're saying there is no energy that was lost, so the total energy remain constant. So that's what we mean. So that's as you can see, whether for example two objects they come together, they are colliding, they separate, then that is elastic collision without them being joined together. So that type of collision, you can automatically clearly see that was an elastic collision. Then when we come to inelastic collision, an inelastic collision, only momentum is conserved. So remember, all the collision, the momentum is conserved because that is a law of conservation of momentum. But in an elastic collision, the only thing that is important there to take note is that the kinetic energy, it's not conserved. So it means it's been transformed into other form of energy, such as heat, sound, or that energy was required for deformation. So you can think about this inelastic collision like a car crashes to one another, then they deform. So automatically a car crash accident, then it's type of inelastic collision because there's a deformation, there's a loss of an energy, that one. So automatically the kinetic energy is not conserved. So the total kinetic energy of the system, it's not going to be equal to the kinetic energy of the system after the collision. So that is what we mean by that. So those are the things that are happening. In most cases, you can see that whenever there's a collision, some of the objects, they're becoming more warmer or more hot. Then that tells you that energy was transformed from kinetic energy to another form. So we classify those type of collision as what? As inelastic collision. Another thing, that how can you see them in nature, as already mentioned about the deform, that you can see the collision where there's a deform. Then you can see that collision where they generate heat and a sound. When there's a sound, especially think about whenever there's a car crash, there's a sound. Then you can see that there was inelastic collision. There's a slowdown more significantly after impact. So for example, maybe in most cases, then the two objects, they become together after collision. So this type of collision mostly are classified as inelastic collision. So that is how you can see them. Then in calculation, then if they're asking you, because most of the time the question is going to come in the format where they're saying classify maybe what type of collision is this one. So it means in order for you to answer that, you must calculate the total kinetic energy of the system before, then you calculate the total kinetic energy of the system after, then you compare. If it's the same, then you're gonna say it's an elastic collision. If it's not the same, then it's an inelastic collision. So in most cases, the question may come in a form where they say prove that or show that the collision was elastic. So how can you show that collision was elastic? Is to calculate the kinetic energy of the collision before and calculate the kinetic energy of the collision after. If it's the same, then automatically you have shown that. So that is what it's very, very important. So perfectly inelastic. So remember, this is still explaining that inelastic collision. So there are two types of collision that we are talking about. Then it's a elastic collision and inelastic collision. Then a special case of inelastic collision, we call it a perfectly inelastic collision. So it's a special case type of the inelastic collision. So this is in a specific case of an elastic collision where the colliding objects stick together and move as a single combined mass after impact. So then whenever objects they stick together after collision, then we can say this is a perfectly inelastic collision. So that is what we are talking about, these types of collision. So that's very important to understand. Then inelastic kinetic energy is not conserved. It's transformed into other form of energy like heat, sound, and deformation. So object becomes smaller or it's just changed the shape. That's what it means by deformation. Then thank you very much.